So I'm Jeremy Gibbons. My microphone is finally connected to the network. I'm going to give you two lectures, one today, one this morning, one tomorrow morning, about functional programming. Everything I talk about is about functional programming. But particularly, I'm going to talk about domain-specific languages, and I'll tell you what they are, and embedding domain-specific languages in a coding language, and I'll tell you what that means. And we'll go through some examples today and tomorrow. We've got some exercises as well. I put the slides online in my Dropbox, and the URL is here. I hope you can all read that. dl.dropbox.user.com/u/5096640/FLOLAC'14 And when they're ready, I'll put FLOLAC'14 tomorrow there as well. So do feel free, if you want to download them, then you can sort of flick back to an earlier slide if you missed something. That's fine. Yesterday evening, Josh and Shin took me out for dinner and fed me weird food, which was an interesting experience. But we discovered we went into a temple, and they had a farmer's calendar of what's a good thing to do today and what's a bad thing to do today for every day from a long period of time. And it turns out that today is suitable for learning skills, according to this farmer's calendar. So I hope that's what you're going to do today. I'm going to teach you some skills. I hope it's suitable for teaching skills as well. So domain-specific languages, they're programming languages. There's a quite a nice book by Martin Fowler, which I recommend. It's interesting reading. It's not about functional programming, but it's still quite a nice book. It's in this Addison Wesley series on object technology kinds of things. There's lots of design patterns stuff in that series. So Martin Fowler's written this book on domain-specific languages, and he defines a domain-specific language as a computer programming language of limited expressiveness focused on a particular domain. So don't mind too much about the limited expressiveness. In fact, DSL designers don't mind too much about that. They don't care if this is not a perfectly general programming language. It's not about making a more powerful language. That's not the point. The point is, it's focused on a particular domain. So you design the language for that particular domain. You target it at that domain. You focus it on that domain, and that comes at some cost. You have to define a new language. That's some cost in the first place, and you're targeting it to the particular domain, so it might not be any use for other things. So you're making a language that you can't use for all sorts of things. That seems counterproductive, but by doing so, you make it a language that's particularly good for this kind of thing. And you can hardwire into your language various assumptions about the domain, about the kind of thing you're going to do. And then there are assumptions in the language. You don't need to say them when you're writing a program in that language. They just come for free with the language. So that means you can write a program in this in a particular constrained domain, and say it much more concisely and much more clearly than if you were writing it in a general purpose programming language. So there are benefits to doing this, and people have been trying to do this actually for quite a long time. You're probably all too young to remember any of these, but in the 1980s there was this move towards fourth generation languages. So third generation languages are general purpose programming languages. So the languages at the time were C and Pascal, but now Java and C# and Haskell and so on. We would call them general purpose languages. They're still third generation languages in some ontology of language generation. Fourth generation languages were basically domain specific languages. So there was a movement to make languages. You might think about web application languages now, or languages for database applications. So they have assumptions about a particular domain of use hardwired in, and they're particularly good for that, and less good for everything else. But earlier, if you're a Unix or a Linux or a command line Mac person, you'll know that the Unix shell has lots of little programs built into it, things like sed and awk and grep and all these gadgets. And each of those is a little DSL. So you can think of grep as being, this is grep, something that takes a regular expression and reads through a file and finds the lines in that file that match the regular expression. Grep is a little programming language, and the regular expression is a little program in that language. And what grep does is it interprets, it runs that program. And what that program means is go through every line in the file, and that's the assumption, that's the domain. Grep is good if what you want to do is go through every line of the file and match for something. So because that's part of the domain, part of an assumption, you don't need to say in your grep program, read in a file, go through every line and do this to each line. That's built-in assumption for using grep. And what you say is something much more focused, just which lines you're interested in. But going back earlier as well, through the 60s, there was various terms that we might now see as domain-specific languages. And even in the 1950s, so Fortran was introduced as a language specifically for numerical computing, translating formulas into programs, mathematical formulas for plotting the trajectory of a missile or weather forecasting and that kind of thing. COBOL for business applications, they're domain-specific languages too. So this is something we've been trying to do for decades. And there are, at the top level, there are two approaches you might take. One is standalone domain-specific languages, and the other is embedded domain-specific languages. And as the title slide suggests, we're going to be looking at the second one. But what's the difference between them? Standalone, you write a separate language. You write a compiler and a parser and a runtime system and so on for your language. So if you didn't have something like Java to start with, then you write a Java compiler and a Java bytecode, a JVM, and all sorts of stuff to do in Java. You write it from scratch in some other programming language, in C or whatever, however you write your Java compiler. And so if you something like grep is the same. So grep itself, program grep, which is the interpreter for the little grep language. Grep is itself a program. It's written in another programming language. It's written in C. The advantage you get from writing a standalone domain-specific language like grep is that you can choose whatever syntax you like. You make up your own syntax. So the people like Jernigan who designed grep said, what's my syntax for a grep program going to be? Well, it'll be regular expression. So let me invent a language for regular expression. And I don't need to be constrained by my prior conceptions about syntax. I don't need to use C's curly brackets or Pascal's keywords or whatever. I'm going to write, the language that I'm implementing will have whatever syntax is best suited to the domain. And the fact that I've written it in C is neither here nor there. I could have written it in Pascal or Java or anything else in Haskell. So the standalone domain-specific language stands alone. It doesn't depend on any assumptions about the host language. And then you reuse everything you know from language design about building compilers and so on. Because you have this freedom, you can make a wildly different DSL from the host language, from the language in which you implemented it. So you might have a host language whose syntax is in diagrams. You might, it's hard to think of very good examples, but you might write a program by sketching some diagrams, and this program works by taking a photograph of your sketch, interpreting the picture that it sees, getting a diagram saying, oh, that's a UML diagram, that means I should do something. You could write something in a diagrammatic syntax if you wanted to. You could even write something in a gestural syntax. Maybe your program is something like a Microsoft Connect box or a sort of Minority Report, and your language is something like Connect, and your program is gestures. You do something like this, and there's a camera pointing at you, and it's interpreting your arm movements and compiling them and running them and doing something with them. So you've got a lot of flexibility with standalone DSL, but it's also a lot of work. So you have to build your own compiler and everything. So an alternative is an embedded DSL. So with an embedded DSL, you provide this new language, the domain-specific language, within a host language, and you provide it just by making some definitions, a library, if you like, in that host language. So then your DSL is a DSL in Java, for example. You just write a class library in Java, and a program in your DSL is a bunch of Java stuff. So now, one of the benefits of this is, well, actually another benefit that's not on there is that it's much easier to get started. It's just a library within Java, so you don't need to build a new compiler, it's the Java compiler you use. You don't need to build a new editor, it's your Java editor you use. You don't need to build a new runtime, it's your Java runtime you use. It's just a library in Java, and when you write a program in your DSL, you're just writing a program in Java, and so you can benefit from all that infrastructure. More than that, you can exploit some of the features of the host language. So if you want loops in your language, maybe you can get away with using the loops that are in Java, and you don't need to invent a loop notation and semantics and everything in your language. If the programmers in your DSL are familiar with programming in Java, then they're already going to be familiar with the syntax of your programming language, because it's just Java syntax. So that all sounds good. That sounds like a very easy way of getting started. There are some downsides. One is that you no longer have the freedom to write the syntax of your language the way you want, because it has to be Java syntax. So you have to be calling methods, invoking methods in Java, writing them in Java syntax. And maybe that doesn't work so well for your domain. You're constrained there. It's still, when you write a program in your DSL, you're writing a Java program. So it's something that's likely to work when your DSL programmer is also a programmer, sort of general purpose programmer, and is familiar with programming languages, and is not going to do something silly with the programming language. Whereas a standalone language, you can write a DSL for non-programmers, for domain specialists. So you can write a DSL for, one example that I saw a couple of years ago was a DSL for lighting design. So if you're putting on a theatrical show, you have lots of stage lights, and if it's a complicated show, these stage lights do complicated things, and you can stand at the front with lots of buttons and turn the lights on and off and hope you get it right for when the actors are in particular places at the front. Or you can script it. You can write some program that will turn the lights on at the right time. So you write a program to do the lighting. That program could be in a lighting language, and the person who writes the program should be a lighting expert. And maybe you don't want to require them also to be a Java expert or a Haskell expert or something. No, maybe there aren't many people who are both lighting experts and Java experts. So designing a DSL for non-programmers can be a useful thing to do, and that's harder to do with an embedded DSL. And sometimes when you're building a library, you're designing abstractions. That's what you do when you design a library in a program. And sometimes the language doesn't let you sort of completely wrap things up neatly in the library, so these abstractions leak, and you have to understand something about the implementation of your library in order to use it properly. So I'm going to, I'm warning you in advance that there are two schools of thought and I'm not really going to dwell on the first school up there, I'm going to focus on the second one. And there are some downsides, but I'll show you how it all works and show you the upsides. And I'll come back to that distinction briefly in a minute. So now within embedded domain-specific languages, where we're just writing a library in a host language, again there are two choices. There are deep embeddings and shallow embeddings. And basically the point of these two lectures is that difference. So I'm going to briefly here, this is the distinction that I'm making, but you'll see this morning and tomorrow morning what I mean by that, because that's what we'll be focusing on, the difference between these two. But in a nutshell, when you define an embedded domain-specific language using a deep embedding, you write programs in that language, and what the program does is very little. It just says, here I am, here's an abstract syntax tree, AST, abstract syntax tree. So what the program does very little. Just you describe what you want to do, and it just sits there with a description of what you want to do. And when you actually want to interpret that program, well, then you have to write an interpreter for it. So you take this abstract syntax tree, and then you turn it into collections of signals that control the lights on your theatre, in front of your theatre. But maybe you want to do other things with that same program. Maybe you want to turn the lighting description, the script for lighting, into a PDF file. This is something that you might give to the producer of the play, or the director of the play, to give them some confidence that the right lights are going to come on at the right time. So it says, at 15 minutes, the two front spots will come on for 30 seconds and something. So that's another interpretation of the same program. It's not driving electrical signals to actual light bulbs. It's generating some PDF output. So you can write different interpreters for the same script in your language. In contrast with the shallow embedding, when you write a language, what the terms in the program in your DSL do is directly their semantics. So you don't build up this abstract syntax tree. Instead, you straight away leap to the output, whatever the output is. You're kind of live coding the lighting. So you're sitting at the front writing some loops, and then the lights immediately, the lights do whatever the lights do in response to whatever you program. So these distinctions will become clearer as we go on, but in a sense, deep embedding is an operational view, and shallow embedding is a denotational view, and that connects with the denotational and operational semantics you've been learning about. And you might say that deep embedding is syntax-driven, and shallow embedding is semantics-driven. And I hope to make that clear. That's the point of these two lectures, to make that distinction clear. But this connects with everything else you've been hearing this week and last week. I want to show you this way of doing it because it's really about functional programming. So if you go back to Martin Fowler's book on domain-specific languages and read what he says about domain-specific languages, Martin Fowler is a well-known writer on object-oriented programming. He's written a book on refactoring, he's written a book on UML, he's written a book on patterns, analysis patterns he calls them. So he does OO stuff. And so to him, domain-specific languages look like domain-specific languages in an OO context. And 9/10 of his book is about standalone domain-specific languages. Whereas if you go to, if you read functional programming authors, or you go to a functional programming conference, and you get something about domain-specific languages, 9 times out of 10, they're not talking about standalone domain-specific languages, they're talking about embedded domain-specific languages. So it seems that different kinds of people like different approaches to DSLs. OO programmers like standalone approach, functional programmers like the embedded approach. Why is that? Well, what I'm going to argue is it's consequence of your programming style. If you're a functional programmer, you'll do it this way because you have these two features, algebraic data types and higher order functions. And if you're an OO programmer, you have neither of these, and so having neither of these makes the embedded DSL approach much less appealing. And I'll hope to explain that to you. I'll tell you why that doesn't work so well. And I'll do that by showing you how it does work nicely with algebraic data types and higher order functions, and that will be the gist of my argument. This is cool. See how we can do it with algebraic data types and higher order functions. What are you going to do if you don't have those? Well, then you have to go read Martin Fowler's book and do it in Java instead. So algebraic data types and higher order functions are two, perhaps the two core features of functional programming. And you'll have had a brief introduction to them. If you haven't seen functional programming before, I will try to be gentle and not assume you're entirely familiar with these, so we'll go through it as the lecture goes on. We'll go through it slowly. But so my subtext, my underlying message really is that functional programming is cool, and in this case it's cool because of these two features, and look, they let you do embedded DSLs very nicely. So much for introduction. So algebraic data types, when you write a program, you build up some structure, and then when you interpret that program, when you work out the semantics, what the program means, what it's supposed to do, it's defined by consuming this abstract syntax tree that you build up. So you build up an abstract syntax tree, and then you consume it. So the observers, these interpretations, are typically defined inductively over this tree structure. The tree structure is recursive. It's the terms in your tree, the trees themselves correspond to programs, so they're finite. You usually don't write infinite programs. The text of your program is finite. It generates a finite abstract syntax tree, and then you define your syntax by traversing that syntax tree, and you do it inductively. You do it recursively following the inductive structure of the tree. And we'll see lots of examples of that. If you want to do other stuff on your language, so if you're worried about the programs in your language running quickly, you might want to do some compiler optimization kind of stuff. And the way that works typically is by taking an abstract syntax tree and transforming it into a different abstract syntax tree. So you write a simple, obvious program, and your optimizer turns it into a less obvious but more efficient program. I'm not going to talk about that at all, but people who do DSLs in anger for a real purpose do often care about the runtime efficiency, and they do pay a lot of attention to these transformations. And that fits nicely into this scheme, but we won't have time to talk about that. There's another reason algebraic data types work very nicely, and that's when you want to write a DSL for something and then connect it to something outside your context. So you're writing a domain-specific language in Haskell, say, because that's your favorite programming language, but it has to connect to some existing system that will actually do the running. So maybe, again, you're a theatre production designer and you want to set up the lighting for your theatre show, and what's the interface to all the light bulbs? Well, it's not a whole bunch of wires coming from the light bulbs into your computer. I don't have many sockets on my computer. So instead, there's a box that runs some other program, and the box is connected to the lights, and I want to connect to the box. The box is an intermediary, and so what I need to do is generate some stuff for the box, not generate some stuff directly for the lights. So I need to take my program and turn it into another program for the box. And how am I going to give the other program to the box? Well, I need to sort of transfer it from my computer to the box. So you need some marshalling mechanism, some way of turning your internal idea of the program into something that you can stick on a different box. And algebraic data types work quite nicely for that too. I'm not going to say any more about that, but there's algebraic data types are quite core to this embedded DSL approach. So here's a DSL. It's a very simple DSL, and it's an embedded one. So it corresponds to an algebraic data type in Haskell. So my language is for arithmetic expressions. And they're very simple arithmetic expressions. They're arithmetic expressions like 3 plus 4 plus 5. I've got numbers, and I can do addition. And that's all I can do in my language. You can't get a much simpler language than that. So that's these are morally the kind of programs I want to express. 3 plus 4 plus 5. I'm going to express them in a slightly clunky syntax. We could do better, but this shows the purpose. I'm going to write my expression as add val3, add val4, val5. So that's the syntax of my DSL. The thing with adds and vals, the line with adds and vals, is a program in my domain-specific language. I say program, but it's just an arithmetic expression. So that's the kinds of programs I want to implement. And I'm going to do it by deep embedding, so I'm going to implement it by an algebraic data type. And this is the algebraic data type. It's so if you've seen this before, I hope. So this is defining a data type called expr D for deep, and never mind the colon, double colon star. This tells that there are two constructors for this data type. That tells you that there are two ways of making an expr. There's the val way and there's the add way. And each of those is a function. Each of them takes some arguments and gives you an expr. That means that there are two ways of building an expr. What they do is they build an expr. And what val does is it takes an integer and makes an expr. And what add does is it takes two exprs and makes an expr. So val takes an integer like 3 and makes an expr out of it. And add takes two smaller exprs and makes a bigger expr out of it. So val takes that integer 3 and makes an expr out of it, so that's an expr. Similarly, that's an expr. That's an expr. And then add takes two exprs and makes an expr. So add takes that expr and that whole thing is another expr. Add takes two exprs and makes an expr. And then add again takes an expr, that's one expr, and another expr, and it makes an expr out of it. So that's an expression too. You might view these things as trees, and this is a drawing of that tree. It's an add at the top level, and the left-hand argument to be added is 3, and the right-hand argument to be added is 4 plus 5. So I hope that algebraic data type is familiar to you. Any questions about that? If you don't get that, everything else is just going to go past in a blur. If you're all right with that, yeah, see those? Do yell if you have any questions. So that's not a very exciting program, and it doesn't actually do anything. As I said, with a deep embedding, when your program just sits there. So this is my program, and if I type in my program, it doesn't do anything. It doesn't, in particular, it doesn't give me 12 yet. It just sits there waiting for something to happen, and you have to say separately what's going to happen. So you might think of that as giving a semantics to your language. So these expressions obviously intended to denote something. The obvious thing that they're intended to denote is integers. Val denotes an integer, and if two expressions each denote integers, then when you add them together, you get another integer. No rocket science there. There is a way of interpreting expressions like this and getting integers out of them. And this program is that interpretation, is that semantics, is that way of processing one of these expressions and getting an integer out of them. So this is what I mean by being inductively defined over the structure. My semantics here is called eval, and the first line says it's a function from expressions to integers. So it takes in an expression and gives you back an integer. And it's defined recursively over the structure. Remember the structure is these recursively shaped trees. And when you define functions over them, the natural thing to do is for the call pattern of your function to follow, the recursive call pattern of your function should follow the recursive structure of your tree. So that manifests itself as follows. There are two kinds of tree. There are val trees and add trees, two kinds of expressions. And so I need to say what eval should do for each of those two cases. If you miss off one of those cases, you haven't given a complete semantics to your language. So you need to say what happens in each of the two cases. And in the recursive cases, in that case, here add is a recursive case, you've got two sub-expressions, x and y, and you typically make recursive calls on those two sub-expressions. You make a recursive call on x and a recursive call on y. And I hope it's obvious to you how this program works. If you've got a val with the integer n inside, what's the semantics of that expression? What integers does it represent? Well, n. This val 5 here represents 5. This one represents 4, and that one represents 3. And what about the semantics of an add? Well, the semantics of this part is what you get by taking the semantics of this part, eval x, and the semantics of that part, eval y. So the semantics of this is 4, the semantics of that is 5, and the semantics of this whole sub-expression here is 4 plus 5, which is 9. Okay? That should all be obvious. And then the semantics of this whole expression is 3 plus 9, which is 12. So that's a semantics for my DSL. So the program in the DSL just gives me an abstract syntax tree, and then the semantics is some function inductively defined over the structure of that tree. And you can have other semantics for it. So here's a different semantics of my expressions. I'm not going to evaluate them and get integers. I'm going to print them and get strings. And I don't think I showed you the output of this. But, that's the so the output of this, well, let's work out the output of this. So this says, print takes an expression and gives me a string. It's a semantics of my language, so there needs to be one case for each constructor in my language. There's a val constructor and an add constructor, so there needs to be a clause of the definition of print for val, and the clause in the definition of print for add. In the val case, it takes the argument and it does the show of that argument. It doesn't give you the integer now, it does show of that integer. In case you've not seen this before, show is the function in Haskell that takes an integer and gives you back a string, the string version of that integer. So print of this will give me back the string with one character in it, character 5. And here I'll get the string with one character in, and here I'll get the string with one character in. If this had been val 13, it will be a string with two characters in, a character 1 and a character 3. And then for the add case, the semantics of this add expression is wrong. So that should have said, excuse me,